Hello everyone and welcome to a special presentation facilitated by IT Masters and Charles Sturt University. My name is Mia Stone. I'm the short courses coordinator here at IT Masters and I'll be your MC during this presentation. Tonight we have a very special guest, Nectar Costadopoulos. Nectar will be talking about the research he is undertaking with Charles Sturt University as part of his Doctor of Information Technology, and he'll discuss his concepts with us in regards to emotion detection and prediction with wearable technology. Now, if you'd like to ask a question or make a comment during this lecture, you can do so using the chat function on GoToWebinar. We will try to answer as many questions as possible. So without further ado, could everyone please welcome Nectar Costadopoulos. Nectar, over to you.
Hello, everybody. I'm Nectar, as Mia said, and thank you for making time to spend your night together with me for 1 hour while I discuss my research into wearable technology and emotional detection. I've got on my second screen, as you can see, I'm switching across a bit. I've got all the comments popping up, and there's a question, will slides be included in the IT Masters site? Basically, I think so. I think there will be, I think Mia will be organizing this. The paper that I've written on this research has already been sent by the email. Or I think at least there will be a YouTube presentation that will be put together. So I think Mia will be best to answer this after the wrap up of the presentation. So I wanted to just first introduce myself, just give you a bit of background where I'm coming from, and then go through the presentation. And I'll be monitoring from time to time the dashboard there and the questions that are popping up. I'll try to answer them the best of my ability. So I'm currently a lecturer at CSU Study Centre Sydney, and I've been teaching a range of technologies, web, multimedia, information systems, cyber, and cyber ethics. And I've become interested in this area of wearables and emotional detection through a range of factors, which I'll explain. I've got a background in arts and communications, master's in information systems engineering, and what I've managed to do the past 2 years is I enrolled in the Doctor of IT program, which is offered by IT Masters, and I managed to do this piece of research, which led to me getting actually a full-time PhD, which I'm pretty much starting now, which I want to look much deeper into this area. Click across. Okay, so this presentation today will have the following sections. I'll talk about some background of the research background, what triggered my interest in this area, and I'll talk about my research method or methodology, the steps that I took to actually collect the data, my pilot project. Then I'll talk about my exploratory pilot project, which collected the data and presented that information that I have in my paper, and then some future possibilities of where we can take this research, which is still in the early days. So when I came to the emotional intelligence field and emotions field from a different angle. I, just like you, got an interest in technology, and it all started when I started seeing wearables come into play in 2012, 13, 14, and especially the Apple Watch, which I'm not sure if you can see. It's a bit you know, it goes blank when you actually try to show someone else. It's a very private type of device, but the Apple Watch and its capabilities, and also Fitbit and other wearables that came out. So I started saying, well, this is amazing. You got all this technology that can capture physiological information about the person, and people were using it for sports and recording performance when they were running. But I thought, can you do something more with it? So I started looking into it, and I enrolled in the Doctor of IT. I started setting up my question, and that's what the first thing that they will try to get you to do is set up a question. I mean, what are you trying to do? And we looked into, can we use consumer wearable devices to sense emotions? And that was important. Consumer wearable devices that cost a few $100s, and to do something like sensing an emotion that has been done in a laboratory setting. Because previous to that, a lot of the tests were done in labs. And then from the wearables, I'm not sure if you can actually see my mouse, but from the wearables, I moved into emotions, and in particular emotional intelligence, which I'll explain next, and then deeper into emotions by going into cognitive neuroscience. So getting into this brain science and stuff. So it wasn't like I studied everything, and once I kind of just started digging, and that's how it happens. You just explore various fields, and I think this area is an intersection of all these multiple areas. So my interest in emotional intelligence, as I said, started by first asking whether I can sense for emotions using wearables. And then that led me to emotional intelligence as a field, which has come out of vogue in the past few years. Like, it was very, very big in the early 90s. Mayer and Salovey in 93 coined the term in a sense. They had similar terms previously, but they really nailed it. And they said, emotional intelligence is about understanding your emotions and others' emotions and using that information to make plans and decisions. So they basically said that it's an important type of intelligence, because previously to that, it was all about IQ. It was all about intelligence and measuring how smart you are. But there's another type of smart, and it's all about emotions. Bradbury wrote an interesting article in 2014. I've put that in the references, and I've got a question here by David. Do you see machine learning and limited AI as being part of wearable technology? Yes. In short, especially where it's going now. The Googles and the Facebooks, they are learning through machine learning. They're creating the patterns and getting the signatures, and then real time they are trying to work out what is taking place. It's still, various levels of development. I mean, as you know, if you're interested in this field, you know that Facebook has been doing research in detecting emotions through people's pictures and faces, and there's many levels you can take this. And the important thing that, going back to emotional intelligence, is emotional intelligence is something that all of us have as human beings. We've got the most powerful computer in our head, in our brain there, and basically we're able to sense things faster than we can actually work out that this is actually happening. So our brain is able to work out when someone is upset. We don't know why someone is upset, but we know something is going on in another person. We're able to detect cues from the person, the way they're breathing or the way they're speaking. I mean, other line of research separate to wearables is detecting emotion through voice, and research has taken place where from the voice you can detect the level of emotion in the person. So Bradbury said emotional intelligence is very important because it's a foundation of host of critical skills that impacts everything you say and do every day, and it's single predictor of performance in the workplace. So from stress tolerance to anger management to decision making, IQ may be good, but emotional intelligence is very important. And being able to understand how other people are feeling. A separate line of research in this field, and I'm getting some questions coming up, a separate line of research in this is helping people with autism detect that other people are feeling upset or sad, because sometimes people with autism have difficulty detecting this. I've got a question here from David. With EQ in my studies in this area, I have found that understanding to include how we emotionally respond to events, our resilience, and how we handle disappointments in the time frame we bounce back from these events. What are your thoughts? Basically, yeah, I agree with you. Emotional intelligence is about detecting how we're feeling, detecting how other people are feeling, and then be able to process that and make decisions. And resilience, and building up resilience. Good managers that are actually emotionally intelligent are more liked by staff members and managers that lack emotional intelligence. So it's not about making quick decisions. It's about reacting coolly in situations and be able to work with people's emotions and be able to be very fine at detecting them. And this is where I'm interested in, especially with detecting stress. Okay, so after going into emotional intelligence literature, I started researching what work has happened before that, because sometimes you are not sometimes you're not the only one that's researched this. It's not, you're not the first. And I actually found that back in 1995, MIT had a group called Affective Computing, established by a lady called Rosalind Picard, and she coined the term affective computing, which involved basically the ability to recognize from a range of physiological, facial, speech recognition, clues about one's hidden affective state. So what's going on inside you, from your heart rate, from EEG signals, from sweat, from a range of variables. And this is a little early diagram, and I've put a link here of the MIT group. So they did a lot of experiments of what they called wearable computers, believe it or not, in 1995. And if you go back then and you remember Windows NT and remember, Pentium computer and 486 and this type of, this is the type of field that they were trying to actually implement wearable technology. See, hypothesized back in the 90s that a computer you wear that attends to during your waking hours could notice what you eat, what you do, what you look at, and what emotions you express. Now, at that point, you would have had to wear a full-on backpack to achieve what we are achieving with Apple Watches and what is coming up in the next few years. So basically, this is what they were trying to do back then, and they were like hampered by the lack of technology. But they did a lot of interesting experiments, which I've looked into, and a lot of that work that's happened in laboratories and using very bulky equipment nowadays can take place with Apple Watches and small EEG headsets. Just got another question from Roy. Have you had researchers before about combining wearables and facial recognition to detect the affective state? Yeah, definitely. Triangulation is very, very important, and in some of the experiments that I've seen, they've strapped everyone and either wearables or sensors, and they've got a camera like you've got the camera looking at me, and from the facial structure, you're able to, get behind the affective state of someone. Rosalind Picard actually has continued research. I mean, she's still actively researching, and there's some interesting TED Talks you can listen to about this. She's been mucking around with very, very sensitive cameras where you can actually detect the heart rate through the actual skin. So just by looking at someone, not only the facial structure, but the heart rate coming through the blood vessels, but just using various filters. So, speech, camera, wearables, the more data you're collecting, the more accurate you get, basically. Okay, so going deeper again, so we keep going we keep going deeper, and I'm sorry, David, but I know you got questions, but I have to push on a bit. Yeah, by going deeper into the field, then I started looking into cognitive neuroscience, which is on a separate branch in a sense. They've got CAT machines and they've got fMRI machines, and they're putting people in these machines and they're strapping EKG, ECG straps to get the heart rate, and they're looking deep into the brain to work out where the blood flow is happening or where there's neuron activity. And they've been trying to understand how the brain works, and be it you're trying to do cognitive tasks or emotional, where the centers of the emotional brain. So people like Critchley, 2005, kind of came up with with a theory that emotion affects the brain and the heart at the same time. And multiple studies have verified that they can detect both changes in the brain and the heart rate in subjects with basic emotions like happiness, anger, sadness, that sort of stuff. So if we look at the first figure here on the left-hand side, what they did in this experiment was a very short experiment. For 1 second, they showed a face of someone, so like someone smiling or angry or something like that. Just 1 second. The brain is faster than we can actually realize how fast. The brain detects something before we even consciously understand that this is an angry face or happy face. Just 1 second. So for 1 second, the face was shown, and then for 7 seconds there was a break, and then another second, another face was shown. As you can see here, these are the rates. This is the heart rate change for a happy face, sad face, angry face, and disgusted face. The top line, the red one, is the angry one. The blue one is sad. The black one is happy, and the green one is disgusted. So the face is shown in the first second. Bang, there's rate of change in the heart rate, and then the heart rate is reduced. So it goes back to a normal state or below the normal state. And then again, another face is shown. At the same time, they correlated it with brain scans. So they showed different parts of the brain, frontal cortex, the back, the sides, and where was main action in the stimulus. So this is not even using EEG cables and the 1020 system. We're just looking deep into the brain and what's going on. And a lot of research has gone into which part of the brain represents which type of emotion. So there's a lot of things to learn there. But all these experiments have been done in, wide lab coats, multi-million-dollar machines, and sampled at thousands of hertz. So there's a lot of data just from a few seconds. And back here we are with wearable technology. So with wearable technology, like my Apple Watch, so right now I'm hovering at about 100 BPM, not 60 BPM, because I'm on full flight with this presentation. So it started with the Apple Watch. As I say, well, this is very interesting. It's a full-on computer. In the 90s, it would have been as big as, it's actually probably more powerful than the computers that they had in the 90s in the Affective laboratory, and it's on your wrist. And the main sensor that I was very interested in using was the photoplethysmography sensor, which detects the heart rate through changes in the blood vessels. So this was first generation, and there's been several generations that have come about. It's still early days. I'm not sure how many of you have got Apple Watches or Fitbits. The problem is batteries. Every night I have to put it to sleep and charge it, and a lot of people find that a hassle. But with everything in the near future, this thing will be able to run for days or even weeks once they sort out the battery. The other technology that I shortlisted was the NeuroSky headband, which can read EEG signals just from one sensor. As you can see, a picture of a person wearing this headband, and there's various different models out there. The gold standard in EEG readings is Emotive, which is about $600 or $700 a headset. But I decided to go really cheap, and I wanted to buy something for $200. and you can get some for $150. So I said, well, the cheapest possible EEG headset, and NeuroSky came around that price, about $200 something, and I think it's about $170 on Amazon now. And that could detect just from your frontal cortex, FP1, a range of brain waves from alpha to theta to gamma, and give me a reading basically of what's happening in your brain. So I was delighted to have this. I've got a question from Amanda. What is a jawbone? I think jawbone was. I think they've actually gone out of business. They're makers of I think Bluetooth headsets for just microphones for speaking, and they went temporarily into running watches and heart rate detectors. I'm not sure how successful they were. I think Fitbit kind of knocked them out, and the winner really. The winner, in a sense, is Fitbit in terms of popularity and market share. But in terms of functionality, which I think you need in a wearable in the near future, is I would say Apple Watch has got better functionality in a sense. Because later on you could load a whole range of applications inside the Apple Watch, where Fitbit is far more limited. So so I decided to run with these two technologies. Again, there's a lot more technologies you can have. You can have temperature. You can have chest straps. There are problems with accuracy when it comes to certain products. So now I'm going to talk about my research methodology, my research method, and how I went about collecting information to try to ascertain whether these wearables can provide us with emotional state of a person. And I chose the two wearables, the headset, the NeuroSky headset for the electroencephalogram to get some brainwave information, and the Apple Watch to get the heart rate information. And I decided to also use a separate method, a qualitative method, to elicit the emotion that the person was feeling, the participant in the experiment was feeling. So I decided to do a semi-formal interview, and I will be asking the person how they're feeling while they undertake a particular activity. I found in a lot of experiments this combination of approach was used. They would, even that happiness and disgust video, they would do a questionnaire before and after. They would ascertain how people are feeling, or they would do an online test where you click on a screen and you choose a set of options. There's a whole way of doing it, but you've got to find out from the person how they're feeling. You can't just collect the information because you can't match it to actual emotion. I've got a question here from David. I think Android-based wearables are going to give Apple Tech a good competition. So LG Urban, very effective. Yeah, the Fitbit ecosystem is very, it's extremely closed in a sense, and I don't like, big thing I don't like about Fitbit, it sends everything to the cloud and you lose control of the information. So if you can load something on a wearable device and collect information at that point and then use it later, that's a much better approach to doing the experiment. So so I used wearables for collecting quantitative data, numbers, and qualitative, how people are feeling. I used an interview method where they would think aloud and go, I'm frustrated, I'm angry, etc. I decided to use a emotional matrix that I borrowed from the Yale mood meter. In emotional intelligence, there is a whole range of emotions that people can express. This Yale mood meter has 100 different emotions that you can actually have at any point. And it's very difficult to ask someone while they're doing an experiment, how are you feeling, and have a very specific emotion. So I decided to just have, a matrix which on the x-axis has pleasantness and energy. So most emotions generally, if you're satisfied, you're on the pleasant side and you're not very energetic, and that also affects your heart rate and other activity in your brain. If you're static, you're on a very big high, that takes a lot of energy. On the opposite side, enraged, that also takes a lot of energy, but you're very unpleasant about it. And if you're tired, you're both low energy and low pleasantness. So I decided to just focus a bit on four areas of emotions there. And again, sometimes it just depends on the subjective understanding of how a person is feeling. If you give them a very complicated word, maybe they don't know how to select it. So you could just say happy, afraid, tired, or happy, afraid, sad, and satisfied, and that would be enough for this level of experiment. So another thing was to test all this. I decided to just run the experiment with about 3 associates and just do a relaxation type of activity where you listen to some music and then a challenging activity. I decided a lot of experiments had people watching videos. So they would watch a video and they would get an emotional response from it. I decided a game would bring some sort of emotional response back. And games can be pleasant or can be very frustrating. So I chose 3 different games that I thought would be suitable for that, which I'll explain later. Another thing is I started doing some experiments. Before you do the experiment, you need to collect some data and just see what the hell is this thing coming up with. Now, when you look at a laboratory equipment, it samples sometimes at 1,000 to 500 hertz samples per second. You're not going to get that currently through wearables. For example, the Apple Watch, Apple is very cagey what it's doing on the hardware level. The only thing I knew, it recorded 12 times per minute the heart rate. That's what it would export as a CSV file. So that's a difficulty. Different devices have got different ways of exporting the information, and basically this type of information coming out, you need to be able to just work out how you can use it. So you're able to then plot a raw heart rate in bits per minute. There's other devices you could use. You could use a chest strap, a Bluetooth chest strap, which would give you a better accuracy. And there's other issues with the Apple Watch, especially how tightly it's worn. And Fitbit was taken to court for having the runners experiencing that it wasn't truly showing the level of heart rate that they had when they were running. Then we went to the EEG device, and the neuroscience device was able to export a range of delta, theta, alpha, all the way to gamma frequency waves using its own power spectrum rating. The device that actually does all the translation from analog to digital is the size of a matchbox, and it's able to kind of do the Fourier transform from the signal all the way to a digital readable power spectrum automatically. That's the first thing. So it gives you the end result of the Fourier transform. You don't have to look at the raw signals. The second thing, which is a problem, it gives you the results in a format that is not standardized according to laboratory situations. So it's not microvolts like most EEG data is. So you can't compare microvolts to microvolts, which was a bit of an issue. So I've got some questions that are popping up on the side there. So what we did with the data, I managed to talk to people in the US at neuroscience and told them there's a problem here because you're giving me arbitrary numbers for EEG data, and they said to me, look, we didn't make it so you can do experiments with it. We're giving you the data, but what you could do is, for example, divide a set of the numbers with a common number, so and create a set of ratios for all the waves. So I actually did that, and I was able to get data that I am able to compare from experiment to experiment. So the actual project. So the games that are selected to elicit frustration was 3 games. The first one, I'm not sure if you've used it, Flow Free. It's an iOS game, and I think it runs on Android too. And it's join the dots type of puzzle where you join the dots and you try to avoid hitting the different dots together. And they've got to be all clear, and the whole board has got to be joined. So it's quite easy when you start with a small matrix. It gets extremely frustrating and hard when you go to a 30 by 30 matrix. So the frustration level, difficulty rises. The second one, I thought Angry Birds. I wasn't sure what type of reaction I would get. It's easier to start, but it can get frustrating, and you have to keep on playing to achieve your goal, and can be frustrating. So I thought that could bring some frustration. And then the third one was a meditation app called Labyrinth. Labyrinths, as you know, normally the physical labyrinths were built for people to walk through and meditate, and it has a relaxing state on the mind. So I thought, would that actually have an effect, a calming effect on the mind? So I was trying to find something the opposite of frustration. And literature in a lot of the studies always indicates that games always bring a range of frustrations in people. So I started collecting the data, as I said, and another problem with the data, 12 times per minute, and my experiment, which is interesting, didn't run for a minute, 30 seconds, 2 seconds. It ran for 60 minutes. So this is the power of wearables. Instead of, people don't have to be strapped into a laboratory chair. It's all Bluetooth or sitting on your wrist. The actual EEG headset is running on Bluetooth, so it's transmitting live data to a computer far away, and there's no need to actually have any wires connected to the head. So the person is free to move. So the experiments ran for 60 minutes. So what I decided was to upsample everything to 60 minutes, to minute by minute level, and also synchronize timestamps. So there was a bit of data scrubbing that you had to do to get the EEG and the bits per minute to actually coincide with the correct timestamp. And with the EEG information, the EEG information did give raw analog information. It gave about 513 values per second. And then it gave the Fourier transfer output, where it had some sort of a power spectrum, which was proprietary and had nothing to do with microvolts, which is EEG outputs generally. And I performed just one more calculation where I was able to divide everything with a delta brainwave, because in a lot of my research, and I'm not sure people's background with brainwaves, a lot of my research was going to concentrate a lot around alpha, beta, and gamma brainwaves, and I was kind of had a narrow approach to what type of brainwaves, because as you know, when you're sleeping or relaxing, delta and theta are kind of like dominant. Alpha becomes a bit more dominant when you are awake and relaxed. Beta starts to get a bit more dominant when you're thinking and you're more active. And gamma is when you're really active and really doing high concentration. So I wanted to concentrate on those higher level of brainwaves and avoid the delta and the theta. So delta I was able to sacrifice and create a ratio for each brainwave for every experiment. So the ratio of every brainwave compared to another. So the changes in the ratios, I could compare one experiment with the other. Then the other thing that the EEG headset would give was a mixture of brainwaves in the form of a derivative: attention, meditation, and zone. So attention is how much attention you have in a particular task. and that was a mixture of, in a sense, beta and gamma brainwave, and meditation, in a sense, the mixture of alpha and perhaps part of a lower beta, maybe delta or theta brainwave. So I was able to give you that reading out of 100, and then the averaging of the two gave you a zone setting, which told you, how a person was feeling. So if you're like stable, your zone kind of like was at a particular high level. These are derivatives that could be used. So there was a whole range of data that was coming in from these devices. And that led to an interesting conclusion that, a one-hour experiment was able to produce a lot of information in terms of 720 records per hour, 1.8 million raw signals in EEG, and 3,600 EEG waves or lines of from the EEG Fourier transform. So all that data just for 1 hour and just from two sensors, and trying to make sense of it was important. Then moved on to trying to map it using graphic methods with the ratios, and this is an experiment, but later on I'll show you the actual the changes in music, or the changes in the various changes in different parts of the experiment. So the experiment took place over several minutes, and I'll just move across to see if there's any questions probably. I've got some questions. How many samples were collected? And the other one is how many were the adult, female, male? Yes, this, as I said, was an exploratory project, so it wasn't an experiment with 36 37 volunteers. It was exploratory to test the equipment, so it was always just with 3 people in a sense, with one female, 2 males. It was just range group from 20 to 45. It was just to test the actual equipment and just collect the information, and then see if there is a possibility to use very cheap wearable devices off the shelf to collect data that you can actually have meaningful research information from it. Because up to now, a lot of researchers shied away from using things like Fitbits and Apple Watches. They used a chest strap, which had a much higher accuracy, or a emotive headset, which costs about $600 to $700, and it's got multiple sensors all over the head, and it's a bit more difficult to install and get it right. So the point of this wasn't to be theory generating. It was just to test the possibility that that this is possible, that you can actually do the research with that. So David is nailed it. Yes. So essentially, you're conducting a proof of concept. Yeah, that's right. And this is what's led to the PhD and the further research into this field. I mean, private companies like Apple, and I've approached Apple and I tried to speak to them about it. Like, they're probably doing this type of research, but unfortunately, a lot of companies, Google is a bit more open about research, but Apple, they don't tell you anything until they've got a product there. Even NeuroSky, when I was talking to the people with the headset, they've got a lot of technology in terms of detecting heart rates and detecting brain waves, and they are always launching new products around meditation and attention and autism disorder and games, and they were a bit cagey too in about what they're doing with it. But what I wanted to do is just can I use this information, and is it meaningful? Can I get meaningful information, and can I corroborate it with current emotions that the person is feeling? So this is a simple graph, and there's a lot more detail in the paper about particular participants. The 3 participants are listed in the paper, and it's got the different graphs. But it had the derivative of emotion, of meditation, attention, and also the alpha, gamma, beta ratios, and how they were changing from minute to minute. The other thing that I wanted to analyze was the heart rate. So the heart rate, as you know, as I was going before, this is the heart rate. This is the heart rate of the person, and when we look at the data, it's not really meaningful. It's between the 90 and 80 beats per minute range. It's bopping up and down. It's not really meaningful. I wanted to extract something more about it. And in the literature, there was discussions about the heart rate changes, but what you need to do is look at the heart rate variation, how it changes relatively to the overall mean. So what I basically did after I collected the data, I was able to calculate standard deviation, mean, and I just calculated the Z-score and turned the Z-score into a positive and negative percentage. And the same heart rate that you see here turned into this heart rate variation graph. So as you can see, there's some major event that took place at 31 minutes. It doesn't look like much when you look at the raw heart rate, but when you go to heart rate variation, something pops positively and negative. And a lot of the rich literature that I read around heart rate variations was that different emotions either raise your heart rate very rapidly or drop your heart rate very rapidly. And all this is around the mean. And there's an effect by some outside influence. And because the heart and the brain is linked together, I thought, can I see some sort of correlation? And in this one, I did multiple graphs. I was trying to map meditation, which is a mixture of alpha and the more meditative brain waves, and the heart rate variation. So when you're relaxed, your heart rate kind of drops down and decreases, but there can be sometimes the opposite effect when you're actually trying to do a task. What really brought it together was the interviews that I was able to do, read aloud method. So as people are speaking out loud and they're playing games. So this is a map of one of the experiments, and you've got the start of the experiment. We start with small piece by Chopin, piano, twinkling music, and the person is just relaxing, breathing, getting used to the equipment, and then getting into the game of free flow where you join the dots, and then moving on to harder levels of the game, and then starting a new game called Angry Birds, playing the Angry Birds, relaxing a bit, having a break between the games, 2-minute break, and then moving through to Labyrinth. So as the experiment was taking place, I was writing notes and I was timestamping what's happening minute by minute level. So everything, all the data had to be upscaled to per minute, and the time steps had to be, I had to make sure that the heart rate was aligned with the EEG data that was coming through. So what I mapped here was the attention and meditation, which is a derivative of the brain waves. And there was like a massive effect by, playing Chopin to this participant. Just all brain waves, there was excitement that took place in the brain. So everything moved at the same time in a very positive spike. And it dropped the moment that the music stopped. I thought that was interesting. I did try to play the same music to other people, to the other two participants, and what I found, they didn't respond the same way. And when I asked them, they found that they were not classical music aficionados that didn't like Chopin. They found it annoying. So it depends on the person. It's very subjective how people react to different situations. And even with the games, I found there was different types of graphs for and different parts of the game. But when they started playing the free flow where you join the dots, the easy part. It's kind of like very meditative because you're just joining the dots, and you're feeling a sense of completion. So a lot of the alpha brainwaves were really doing well there. We started getting into more difficult territory, and what I found before, as you're getting into more difficult territory, your beta waves and your gamma waves were getting increasing, and that was also pushing your attention because you're trying to fight a particular problem there. And in a lot of the cognitive neuroscience literature that I was reading, I found that what was happening, people's attention would drop when they had given up, or their, in a sense, the gamma and beta brainwaves would kind of like drop down, decelerate, and alpha would be increasing. At the same time, when they should be really concentrating, alpha would be increasing. And I found this was happening. At the really harder, frustrated areas of the game. The person would fight, but then they would say, "I'm really angry, I'm really upset, I'm really frustrated," and then their attention would drop. And it was really incredible to actually see that as they were actually speaking. So they started, Angry Birds would get people's interest up and running, and actually it turned out to be very relaxing. Angry Birds turned to be a very relaxing activity, and this the meditation was really high up when they were playing this really loud game where you're just smashing up birds and stuff, and attention would spike up and down. But as you got into the harder bits, it was interesting again to see that spike, beta and gamma radiation, brain waves just increasing, and then dropping, and then increasing again. It was almost like your brain is just trying to crack the problem. And you could, what I was trying to detect is this points of frustration? Is this really erratic increases and decreases in beta and gamma brainwaves? Is it just like a signature for frustration? I found it very interesting. But you needed to corroborate. You needed to timestamp and look at what are people doing. What are people doing at that point? How they're feeling, and talking to them was very valuable. Doing that, and then Labyrinth. If you can see Labyrinth, it's quite interesting. It's very interesting. With Labyrinth, everything just quietened down. Literally, if you look at the zone, which is the mixture of attention and meditation, it really flatlined. They went into a groove and they were able to just finish it. It wasn't frustrating. It wasn't it was just relaxing, and there was some sort of synchronicity of the brain waves, and in a sense, if I go into the heart rate, everything quietened down. The peaks and troughs were happening in the earlier part of the experiment, from 44 to about 8 minutes, from 8 minutes to 44, and then kind of quietened down. So it's interesting. Different types of activities listed different types of heart rate variation and activity. But this was a key. You got to talk to people and work out what are they feeling, and then try to corroborate it and try to see if there's actually a pattern. There's a comment by Radzikanan. The heart rate variation and the correlation frustration should be vary from people to people, gender, different age, and different situations. The literature is actually pointing towards that. That's what I'm reading in the literature, and younger people, like the 20-year-old that I got to play, they found Angry Birds just easy. You could even tell that the brain wasn't working at all. It was just, yeah, whatever. But older people that they've never really played with Angry Birds. They were just lost. Where do I click? Where do I touch on the screen? And you could see they were getting more frustrated. So it is a subjective experience. You know, it's a subjective experience. What makes you stress? One person is cool as a cucumber. Another person is actually very, very stressed and not very relaxed. But what I'm saying in this, I'm saying that, you know, when we look at the heart rate variation, and if I look at this graph, I'll say, well, something has happened between 30 minutes and 37 minutes. Something has happened. What has happened there? Generally, there shouldn't be too much movement in heart rate. There shouldn't be if there's too little movement in heart rate variation, which is very interesting. If there's too little movement, that can actually indicate that you're very stressed, because natural heart rates move up and down. If it's very constricted between a range, it means you're stressed. It means you are tightly breathing. There's many factors that are linked together with your heart rate. But if you're very excited, it could be very happy, or you're extremely angry, your heart rate will also go beyond particular bounds. So the actual response is different from person to person. And that's a challenge when you're trying to do machine learning. David, again, I wonder if there's a relation between certain brainwaves and the frequency of different music. Yes, that's very interesting. Chopin, Mozart, you know, studies have happened, you know, affects your alpha brainwaves and gets you into really productive mood. If you're listening to heavy metal, I think it will have a very different effect on your brain. Very interesting. Again, there's so many experiments, so many levels you can take it, but the equipment is just cheap. So future considerations. Currently, there are gaps in the literature, but this is coming over and over again. That, you know, some wearables, especially Fitbit, got in trouble for accuracy. I did a small experiment actually, and I published at a conference where we did with a chest strap, and we did find the chest strap was 15% more accurate than the Apple Watch, and we did find the type of activity had a big effect on accuracy. So while I'm sitting here, it's telling me my bits per minute, it's 86 bits per minute. But if I was running and I was moving my arm vigorously, I couldn't really trust that result as much. And this is the problem with photoplethysmography. This is the problem with it. And how it actually attaches the skin, whether you got a tattoo, etc. But when we're looking at this, well, I'm not looking at, I don't care whether it's 86 or 80 or 90. What I'm looking is changes in this heart rate over a longer period of time, and that can actually smooth out the situation. I'm looking at changes, whether it's staying high for long periods of time or dropping suddenly. So this could be maybe not a problem if you don't care about being very, very accurate in terms of what is the bits per minute. The other thing was that the sheer amount of data. So, you know, 3 experiments produced 5 million lines of EEG data, and you know, and this it can be trouble when you're trying to do online real-time detection of emotions or any type of work like that. So you need cloud computing, you need very fast internet connections. So there's a whole range of technologies that need to be developed to handle this barrage of data. And this is just from 2 sensors. And if you had more sensors, you would have a bigger problem. And once these models and apparatus has been developed, you could have in the future a lot of interesting applications. I'll talk about one next, but like from organizational perspective, if you knew that your staff members are stressed in a particular situation and they have they've got elevated heart rates and heart rate variations particular times of the day, and high gamma or very high alpha when they should be really productive. One thing, a little telltale sign is when someone should be actually working hard, alpha should not be high. There's two things that can be happening. The alpha brainwave could indicate that they're doing nothing, or they're so stressed they're just tuned out completely of what's going on. Like what happens when you're at a meeting and you're completely bored, you drift off, you daydream, your alpha brainwaves go off the scale, which could be a very difficult to do in the future, in the near future, daydream during a meeting or even an online lecture as such. Some more comments here. Justin, what about visual impairment? They obviously have emotional intelligence. Yes, this would be very interesting research actually. People with visual impairment, whether they can use it because of loss of sight. When you look at someone, as I said, the brain actually operates faster than our consciousness. So when you look at someone, you know someone's upset or angry just by looking at them, and by not having eyesight, that could be a problem. So you could have technology that's actually speaking to you and detecting for you. As I said, in autism, there's a lot of work with this type of devices to help them understand themselves and understand other people, how they're feeling. So that's an interesting line of inquiry there. And also, auditory impairment, definitely. You're taking me on a tangent, Justin. I was just reading in the media about like some Kickstarter campaigns and some of the latest wearable trends. Now they're trying to get away from wearables, and this whole category of hearables is out. So there's like an earpiece you can wear on both sides, which is Bluetooth enabled, 32-bit processor. It's able to detect your heart rate, your steps. It's able to talk to you. You're able to load 4 gigs of music into it, and it's waterproof up to 1 meter. So you don't need Apple Watch. You just put your hearables on, and off you go. And there's some even work in getting an EEG sensor that's able to detect some brainwaves in your ear. So in the future, you may not even have any wearables that you're wearing. You're just wearing them in your ear. And if Elon Musk gets his way with his brain implant, you can imagine that's going to be a lot of rich data. But that's a long way down the track, I think. David, again, for the workplace to be doing this, I would think they'll have to have a policy on privacy consideration, opt-in agreement for employees. What do you think? I think, yeah, a whole rearrangement of enterprise agreements will be necessary. There's been an interesting experiment that's actually happened in the US, where they actually handed out special dedicated wearable watches which detected heart rates and sent them up to a central server, and they were able to basically collect stress maps of particular areas in an organization and in a city. And they say in the near future you'll be able to as part of human resources policy to detect whether there's elevated stress levels in different departments, and then force a particular investigation of why this is happening. If a whole department is stressed relatively to other departments, perhaps it's not the workers that are at fault, but it could be management. And there could be quantitative evidence that people are working too hard. So this is where we're heading with this type of technologies. Once big data and this, it's able to get that data into some sort of a format that can be used. And come to this scenario, Martin Hell asked me to do this presentation initially and said to me, this is fascinating. He was at the presentation, he listened, he was interested in my research, and said to me, how about in the future, let's say in 2025, you're doing a presentation like I'm doing, and during the presentation, you can see the different levels of emotion that your participants are feeling. At this point, you know, imagine I'm kind of flying blind. I'm using the comments and the questions as a way of gauging how you as participants are feeling about this presentation. But if I had like some sort of a worm or some sort of a chart of all of you, and it's, you know, attention's going up or it's bored, you know, then I could be changing my tone, because when I'm in a room giving a presentation, I'm watching people and I'm adapting and changing my voice, and again, a whole range of privacy issues. And, you know, we're not there yet. All the wearables are proprietary. They're not communicating with each other. There's no standards. Fitbit, as I said, grabs your information from your watch and sends it to the cloud. Then you can see it. It's stored somewhere in the US. You can export it as a CSV and do whatever you want with it, but nevertheless, it's taken and put onto the cloud. Apple keeps it inside the Health app on your actual Apple Watch and then goes onto your phone, and you can export it or export it to an app or a CSV file. Every wearable company is using a proprietary method. So to achieve this, we would need to have some sort of a global standard of wearables communicating, and you need some sort of an AI, machine learning, something like that to be able to provide what Martin Hell is actually saying, a real-time chart of how people are feeling right now. Yeah, it'll be fascinating if you can have that. Okay, yeah, people are saying thanks for the webinar, and it's getting a bit creepy. Yes, yes. So it's, you know, one of my areas is cyber ethics. So I'm also very interested in the ethics of this, and differential privacy is a huge area in this field of wearable technology, where you are able to hide individual aspects of the wearable data and only provide a subset of that information to other people or other entities. So how you handle the information is very, very important. Fitbit has disappointed me in a sense. I used Fitbit for a while, but I was scared because everything just goes up to the cloud and you lose control of your information. Apple gives you the control by storing it locally, and you decide how to export it. And they're going to localize AI onto your device to a degree to process it locally. I think that could be the way forward with this information. So my journal article was actually attached to the actual email, so you've got a copy of that. And I've got some further references, but again, all these references are available at the back of my journal paper, which you can access. Well, thank you, people. I hope you had a good presentation. I think Mia will probably take over.
Thanks, Nectar. It's been a pleasure to have you on board with us. Your research has given us plenty of things to think and talk about. But Nectar, most of all, we wish you all the best with your continued studies. Please keep in touch with us here at IT Masters and let us know how it all goes.
Thank you very much.
Thank you to everybody for staying tuned. We will make this recording available to you tomorrow, and you will receive an email with all the relevant details. Now, before we sign off, we do believe that there is real value in continued education, and CSU does offer a unique IT doctorate that is industry relevant. It's the same one in which Nectar is doing at the moment. Now, undertaking your doctorate is a big commitment, so we here at IT Masters have a short course available to you which gives you a better idea of the kind of skills needed for research. The short course is free to undertake and no academic qualifications is required, but if you are interested in commencing the IT doctorate through CSU, there is some criteria that you will need to meet. We do encourage you to give it some consideration and request that you speak to one of the course advisors about your options. You can check out the DIT short course by visiting itmasters.edu.au, or you can check out the Doctor of Information Technology through CSU by visiting csu.edu.au. Well, that's it from all us here, and we will now end this presentation. Good evening and good night.